So this is my major assignment A1 video. Our problem statement is that a brick wall of alpha 4.72 times 10 to the negative 7 meters squared per second with a thickness of 0.5 meters is initially at a uniform temperature of 300 Kelvin. Determine the length of time required for its center temperature to reach 425 Kelvin if its surfaces are raised to and maintained at 425 and 600 Kelvin. These are the equations we're going to use for one-dimensional heat transfer. We're going to rearrange this first equation to solve for the temperature. We are also going to use a stability criteria. For it to be inherently stable in one dimension, the criteria needs to be less than or equal to 1/2. For the sake of ease of this equation, we are going to assume that our stability is 1/2. So we can go ahead and make that equivalent to 1/2. And over here, of course, since we're multiplying it by 2, this will be equivalent to 1. 1 minus 1 is 0, and this entire back section becomes irrelevant. So we have just a simple equation up front here to deal with. The initial values were given. Alpha is going to be 4.72 times 10 to the negative 7. Our delta x is going to be 0.5 meters. And then our delta t, we're just rearranging our stability criteria, and we're going to solve that to be 2,648.31 seconds, and then converting that to 0.74 hours. We are also told that our left wall is going to be maintained at 425 degrees Kelvin. Our middle section of the wall is going to be initialized at 300 Kelvin, and the right wall will also be maintained at 600 Kelvin. And then our overall goal is to get that middle section up to 425. So to first start solving this, we're going to set up our Excel file. I have my dx at the top as well as my dt and my alpha values. Then I went ahead and set up the boundaries of my graph with the x values increasing by our dx and the time increasing by our dt. I have it in seconds here and then hours over here just for ease of viewing purposes. Then for each one of these sections here, we have our left wall boundaries, our right wall boundaries, and then this middle section that we are looking at for changing values to reach that 425 Kelvin. For each of these values in the middle, we are using our equation of 0.5 times the temperature plus 1, and then plus the temperature -1, both of those multiplied by that 0.5, and we're able to find our temperature at this particular point in time at this stage of the wall, and we do that for each one of these stages all the way down until we find 425. And it looks like we reached 425 right in between about 16.5 hours, maybe when we would expect to reach a 425 degrees Kelvin within the center of this wall. And to just further do this, we're going to plug this into Python. To do this, I imported matplotlib and numpy as well as my Excel document into Python and activated my worksheet. For the x values of my plot, I took just that first column, which is just our dx. Y was a little more complicated because I wanted those y values to change with each time increment. So we ran a while loop so we could get each of those values, and it would create a plot at each time increment. And this is what those plots put together looks like, and it's able to show us that heat transfer rate over time. We're able to see this point right here would be our middle section of the wall, and it reaches that 0.25. It's just a little bit above 0.25 at just shy of 17 hours. And we're just able to see the overall flow of heat through the entire wall. And the stability criteria, we used it equal to or less than or equal to 1/2 for the one-dimensional heat transfer, and that's because our temperature values that we were using were only left and right values. And the stability criteria is used just to make sure that we don't have a huge oscillation in our t values, so we don't have big variances in our calculations versus the actual values. So we want to keep it as small as possible. So we're going to have to get a tighter and tighter range as we go from 2D to 3D, just because we have more t values that we're dealing with based on the increase in dimensions. So for 2 dimensions, we have left, right, top, and bottom, and then we add front and back dimensions for that 3D.